Hello, yeah, this is the next part of the 2017 Oxford Pat. I'd like to think this would be the last video, but considering how difficult question 18 was, if they carry on like that, I might need 2 more videos to finish this off. Let's carry on with question 19 then. So we've got a curve defined parametrically like this. Non-zero constants. What values of x is y equal to 0? Okie dokie. Right, no, I was just hesitating. Yeah, we're not going to be merging these. It looks far too complicated. Let's just get when y is 0. So y equals 0 when we've got these things are the same. So when cos omega t equals √3/2. So that's when we're getting y is equal to 0. So that is going to be when omega t is equal to, well, that's our 30 degrees. So our pi by 6. And then we've got to go to a minus pi by 6, so 11 pi by 6. So we got those, but it's going to cycle around. This is going to happen every time, isn't it? So we're going to be adding 2n pi's onto all of these, plus 2n pi, where n is some integer, for n is integer. Okay, now we can just stick these into x, and then hopefully that's just going to be it. So x has got to be equal to, so we'd have a, then we've got omega t, so that's just, so we've got pi by 6 plus 2n pi minus sine omega t. So the 2n pi bit isn't going to affect that because it's just cycling at the same rate. So we're going to have sine of 30 is a half, so minus a half. So that's one option. Or we're going to have a, what is it, 11 pi by 6 plus 2n pi, and then that's going to be, well, minus a half, so minus a half plus a half for n some integer. Right, so that was, we got more marks for that than we did for question 18. Seems a bit weird, but still not going to complain. So that's question 19 done. In a certain binary star system, 2 stars with identical mass m have equal and opposite velocities v2 on the opposite sides of the same circular orbit radius r. So we've got some mass m, equal and opposite. Right, okay, so they're both doing v2. They're same circular orbit radius r. Right, these are both m's. That is radius r, okay. In another system with 3 identical stars of the same mass as before, it observed that all 3 stars are equally spaced around a circular orbit with the same radius r as before. Right, what is the speed v3 of these stars in terms of v2? Right, so now we've got m. These are all moving v3. Okay, that's at radius r. These are still m. So we've got on these then, so we've got circular motion we're wanting to put in on this. So we're going to have for v2 then, so for v2 circular motion, that means that we're getting the gmm, so gm squared over r squared, which is 4r squared, because the force is 2r away, the distance between the masses. That's our gravitational attraction if we've got, you know, that F going towards the center, and that has got to be equal to mv squared over r, so mv2 squared over r. So that gives us that, so v2 squared is, we get rid of m's, we get rid of r's, is just going to be gm over 4r. Right, that's good. So let's scroll down. So for v3 we can do the same thing, but now we've got the force, we've got 2 components of the force going off. Right, so we've got to work out what our angles are on all of these things then. So that's going to be, this is an equilateral triangle, so that's going to be 30 degrees. So we're going to have 2f cos 30. We'll think about f in a minute. That is going to be equal to mv3 squared over r. Now we need to know what f is. So f is going to be, well, it depends what that distance is. So we've got that. So we need the distance between these things, don't we? So we've got well, that, let's make those triangles there. So we've got an r cos 30 is half of the distance between. So that's an r root 3 over 2. Double it. So we've got a root 3 times r is the distance between them. So f is going to be, what are we doing? GMM, so that's a GM squared. We've got a root 3, so we're squaring the root 3. So we've got r squared times 3. Okay, so that's good. That cos 30 is another root 3 over 2. So that's going to cancel with that and leave us with a root 3. Right, so we're doing that v3 squared is going to be root 3 times f times r. So that's gm squared root 3 over 3r, because one of the r's has cancelled. So that's looking good. What does that leave us with all of this then? What am I doing? How do we put that in terms of v2? That is equal to, oh no, I've got to cancel an m as well. Nearly left in an extra m, but we've got this m sitting here that we need to cancel on both sides. So if we were going to have, what do we have to do to v2 squared to turn it into v3 squared? We need to multiply it by 4 root 3 over 3. So that's v2 squared times 4 root 3 over 3. So what are we doing? We're doing v3 in terms of v2. All right, well, we're pretty much there then, aren't we? So just scroll down a little bit more. So v3 is equal to 2v2. And then we've got the square root of root 3 over 3. There you go. Oh, that was another one. Well, that looks as though it was going to be a lot more difficult than that. But it wasn't that bad. It was just a sort of fairly basic mechanics question with a little bit of geometry thrown in. Again, 9 marks. I know that was more difficult than the last question, but compared to question 18, I think I'm going to take a while to recover from question 18. Question 21. Evaluate this expression. Right, okay. Right, this looks like an okay 5 marks. We can do the 9 marks. We can do this in either order. Let's do the integral first then. So we'll have d dt of, so what's that going to be? We're integrating with respect to x. So that's going to be, well, that x to the 4, the t we're not changing. So we're going to have x to the 5 over 5 multiplied by t to the 4 from 0 to t 2t squared. Right, so the 0 we can ignore. So we need to do d dt of all of this. So we're going to have 2 to the 5 over 5. And then what we got, t to the 14. Okay, so that is going to be equal to 14 times 2 to the 5 over 5 times t to the 13. Wow. So t to the 5 is, that's 32, isn't it? So it will be 480 minus 32, which is 448 over 5 times t to the 13. Right, they've gone back to the easy stuff again on these. Now we've got equation of circle 1 is that, equation of circle 2 is that. Sketch a diagram of these circles on the axes below along with the lines which are tangent to both circles. For each line, calculate the length of the line segment joining the tangent points. Right, this sounds fun. Right, if we're going to turn this into circle, well, it's divide by 4 on this. So let's get that gone. That's a 6. That's gone. That's a 4. That's over 4. So when we complete the square on all of this, we're going to get the center of this one is going to be at -3, 2, because we're just halving those coefficients on x and y. And the radius is going to be the square root of 9 plus 4 minus 43 over 4, which is 10 3/4. So that's 13 minus 10 3/4, which is 2 1/4. So square root of 2 1/4 is 1 1/2. Right, so that wasn't so bad. Second circle, get rid of the 4s again. That's a 10. That's gone. That's a 2. That's over 4. So on this, we're going to have center is going to be at 5 1. And we're going to have the radius is the square root of 26 minus 79 over 4, which is 19 3/4. So that's 6 1/4. Oh, wow, okay, they've given us some nice numbers, so 2 1/2. So we got those, so let's draw those on. So that's -3 2, which had a radius of 1 1/2, wouldn't it? So it's going to go up to 3 1/2 and down to 1/2. So let's make it maybe a little bit bigger than that. So we're going to have a circle like that. And then the other one was at 5 1, wouldn't it? So let's say around about, I don't know, there, with a radius of 2 1/2. So that's also going up to 3 1/2. And then there and sort of down there. So we're getting that sort of look. Okay. Well, that's made things, what was that? That was 5 1, wasn't it? Yeah. And 2 1/2. Well, that's made things a bit easier, because if we got to get these tangent lines, right, well, let's draw on the tangent lines. I'll go to a different color. So, but we know that this one's flat at the top. It's just going straight through 3 1/2, because we've just seen that. And so that's going to solve a problem for this one as well, because we've got that pair of what we could, I suppose, say the exterior tangent lines. They're going to be identical because we've got a line of symmetry going through the center of the circles. So these must be the same. That's going from -3 to 5. So these are both of length 8. So they're both length 8. But then we've got these interior ones. So say we were doing that line, just going from there to there. And then we'll have the same on the other side. This is a really difficult direction to draw a line in on this screen. So we can see these are shorter. So how are we going to go about doing these? We've got our right angles there, and we can draw, well, line of centers is going to help. So we've got these triangles kicking around. We can work out what we got. That's 1 1/2. That is 2 1/2. Oops, 2 1/2. And we can work out, oh, we'll be all right then, won't we? Because we can get the distance between the centers. So what's the distance between the centers? Distance of the centers is going to be, we got a change in y of 1 and a change in x of 8. So Pythagoras is going to give us root 65. And we know these triangles are in a ratio of 3 to 5 for the triangle. So that's this triangle here and this triangle here. So that means we can, if we work out the one of these sides, say that side there, then we multiply that by 8 over 5 and we've got the distance between the tangents, because that's the ratio that we've got there. Right, so yeah, to clarify what I'm saying with all of that, let's scroll down a bit and draw this out. So say we were looking at this triangle from the big circle. So we've got a radius of the big circle going across to this point here where everything's intersecting, and then back to the center of the circle. That's our right angle. We know that's 2.5. This is going to be 5/8 of root 65. And this is going to be some distance x. At the end of it all, we're going to want to get the tangent distance, the thing we're trying to work out, is going to be, well, we need to now scale it back up because that's going to be 5/8 of the tangent distance. So we're going to need to multiply it by 8/5 at the end, and that's what we're working out. So we can say that x is equal to, or x squared is 5 squared over 8 squared times 65 minus, so 2.25 is what we got on all of this, isn't it? 2.5, sorry. So yeah, 5/2 squared, so 25/4. Right, so we got all of that. So we need to square root that and multiply by 8/5. So the tangent distance is going to be 8/5 times the square root of 5 squared over 8 squared times 65 minus 25/4. Wow, okay, well, actually, no, this is going to be a lot easier if we take that. Right, I've got to scroll down again. We take that 8/5 on the inside, it's going to cancel with the 5 squared over 8 squared. So we're going to have the square root of 65 minus 25/4 times 8 squared over 5 squared. So they're going to cancel. 8 squared over 4 is 16. 65 minus 16 is 49. So we got 7. Right, so that's come out really nicely in the end. And is that everything they wanted? We've done the sketch. For each line, calculate the length. So we've got 2 of them of length 8 and 2 of them of length 7. Yeah, that's not bad at all. So, right, again, this has taken up quite a lot of time. These are actually, these questions have been quite good fun. They've been a lot easier than question 18 that we wrapped up the last video with, but they still haven't been super duper easy. That one was quite tough. So I'll end this video here, finish off in the next one.